Hey guys, welcome back. In last lecture, we had an overview about how we measured complexity of an algorithm. In this lecture, we'll see some basic complexity values that we mostly use to show complexities in different cases. Let's look into these common growth rates. We'll move from the most performant to the worst one. And the first one is constant time. Constant time means a function or an algorithm will always work in the same way, irrespective of input. For example, if your function is adding 3 to the first element of this array, it will be executed in constant time. In this, we are accessing the array element on the specified index and then adding 3 to it. Now it doesn't matter of what the size of the input or the size of the array is. If it will be 1,000, million or billion in size, it won't affect the execution time of the function. It will anyways be constant. Why? Because we don't have to iterate through the array to get to that index. We already know the index and we're just getting the value from that index and then adding 3 to it. If we show it in a graph for any value n, the elementary operation will be constant. So it will be just a straight line. One thing to notice here is that the 1 in O1 is not the exact number of elementary operations. You might think accessing an element includes 4 elementary operations, as an int takes 4 slots in the memory to get stored. And adding it to another integer again is another operation. It should be a number like 08 or something. But it is not like that. We don't care about how many operations it's gonna perform. Instead, we compare the performance with growth of input, and since O1, O2, O3 and so on doesn't have any relation with the size of input, so we write it like O1. Every operation which is not depending on input is considered a constant time operation, like addition, multiplication, accessing any data, returning result. These all are constant time operations. Next is logarithmic complexity. Logarithmic or log n complexity is also very powerful. However, the best one is constant time complexity, because constant time complexity does not vary if input changes or input increases. This logarithmic complexity is also good because it does not increase as fast as the input increase. Let's look into it. If we know about logs, log of any number x with base b is equal to y. This implies that b to the power y will be x. Yes, I know we are getting into maths now, and that's why most of the people are always scared of logarithmic complexity and don't really know what it means and how it works in complexity analysis. But trust me, once we get the maths and concept behind this, we'll understand logarithmic complexity a bit easily. So this is what log actually means. The base b here is important, like log base 10 of 10, and log base 3 of 10 will be having different value for sure. Generally in mathematics, if you remember, we work with base 10 mostly. But in complexity analysis or even in computer science, we take binary log, that is base 2. As our system works on binary representation of data, it stores data in form of 0, 1 in memory, so computer works on binary log. That means log n is equals to y implies that 2 raised to power y is equals to n, because the base is 2 here. And that means log 4 would be 2, because 4 is 2 raised to power 2. Log 8 will be 3, because 8 is 2 raised to power 3. And log 16 will be 4, because it's 2 raised to power 4. So look at the growth in n here. We are doubling n, but binary log of these is increasing by just a tiny amount. This is increasing by tiny amount, which is 1, as we are having 2, 3 and 4 here. So if we tie this back to complexity analysis, If your algorithm is having log n complexity, that means your number of operations or number of memory slots used by the algorithm increases with just a tiny amount even when you are doubling the input size, which is incredible. Now look at this graph. Initially it increases a bit faster, but as the input increases, it just increases with tiny amount. And at very larger values, it will be almost like constant. It is indeed what we really wanted. For instance, input is 10, then number of operations will be 3. If the input is increased to 100, the number of operations will be 7. And then if the number of input size grows to 1000, the operations will only be 10. So for a million input size, see the difference? There you see only 20 operations are required. And for a billion, only 30. So you see the difference in number of operations with respect to the increase in input. It is going towards being constant. Let's take an example. Suppose you're having an array and your function is working like at every step it is eliminating half of the array. For such algorithm, if your array size is 4, it will take 2 steps to execute. So it will be log 4, which is 2 steps. And now if you double your input size, then it will just take 1 extra step to cut it in half. And the total steps would be log 8, which is 3 steps. So functions having log n complexity are very performant. However, I'm again reminding you that best one is constant time complexity, but next comes this logarithmic complexity. Another perfect example to logarithmic is binary search implementation, where at every step we deal with half of the tree nodes. Now let's move to next complexity, which is linear time complexity. In this, runtime taken by function increases in linear manner as the number of input increases. We do write such code often that has linear complexity, like using any loop. It can be a for loop, it can be a while loop. For example, iterating over an array. This will include n time iteration through the array. For input size 10, 100, even for 1000 it's still decent because 10 at 10 it will perform 10 operation, at 100 it will perform 100 operation, at 1000 it will perform 1000 operation, but at input size like a million or a billion it will definitely get slow and will take more time. So the algorithms having O(n) complexity are quite good and acceptable, but yes, at larger input size, they're not much performant. That you can see in this graph, it increases as n increases. So this was linear time complexity. Now complexities after this are a bit horrible. Next we have quadratic time complexity. It is, as you can see, is O(n) square. So in this type of complexity, the performance of function is directly proportional to the squared size of input data. For example, whenever we are writing a loop inside a loop, this complexity will occur. Like if you are given an array of size 10, you need to find the duplicate in this array. For this, a nice solution will be something like iterating through the array and iterating again. Compare the outer iteration element to inners, and if both are equal, you get the element, you and both the loops. So for 10 elements, it will perform 100 elementary operations, and for 100, it will perform 10,000. So it is just squaring the value, thus taking n square iterations. So if your input size is 1000, then iteration will be 1 million, which is not acceptable. So this is O(n) square complexity. Its graph grows like this. There are also ON cube, ON4, these kind of complexity. That means more and more nested loops in your function. That slows down execution even more. Even worse than this, we have exponential and factorial complexities. Exponential complexity is 2 raised to power n. That means number of operations increases exponentially as you increase number of inputs. For example, whenever we implement loop inside recursion, where function calls itself, so in that case, it increases exponentially. Yeah, terrible. And worse than this is factorial, which is n multiplied by n minus 1, n minus 2. It goes on until value of n becomes 0. So like we have recursion inside a loop for n minus 1 times, we get such terrible performance. So these were the most used complexities that we come across while coding and writing algorithms. Now, while solving any problem, you might get the case where our algorithm is having complexity mix of these values, like iterating through any array in forward and backward direction, that will be 2n, and performing some constant operation along with that, which will be O1. Now to solve this, we don't need to take these constant values 2 and 1, as ON is much bigger than these, so it will not affect the overall complexity of the algorithm that much. So we will be having ON in this case. Similarly, if you have complexity like ON square plus ON, then you can eliminate the ON here, because at larger values of n, ON will be nothing as compared to ON square. And in equations like this, we are having O n raised to power 4 O n square plus O log n. This can be written as O n raised to power 4 plus n square plus log n. So here log n and even n square can be eliminated, because with larger input size, the value of n raised to power 4 is much larger compared to log n and n square. So from asymptotic analysis point of view, this complexity can be written as O n raised to power 4. Another important thing to mention here is that suppose you have more than one type of inputs and your algorithm is having complexity like O n square plus O m, or something like O n raised to power 4 plus O log m. As both of inputs are different and cannot be compared and eliminated, in these cases the complexity will be O n square plus m and O n raised to power 4 plus log m. Alright, so that was all about this lecture. Hope you have a better idea of complexity analysis, the key complexity values, and how we can calculate complexity of any algorithm. Complexity analysis was the fundamental concept that you must need to know before actually learning the techniques to write algorithms. Because you should know what solution or which solution is better and efficient to execute. It's actually quite simple if you think whatever problem you are solving, your solution should be efficient on larger inputs, because with time, data increases gigantically and our solution should be decent enough to handle that. Therefore, having a good knowledge of complexity is mandatory. From next lecture, we will start discussing on basic algorithm design techniques. So see you guys there in the next lecture.